Again, good morning for those who are watching us on the recording. There was a question, actually, I don't know if it's from your class or somebody else's class, and that is related to the recording themselves. And the fact that apparently Zoom records them and posts them in the Confer Zoom. The trouble with that is that sometimes basically it times out, so it starts a new recording. And now you go and watch them, at least for some of my other classes who were confused, which one is the first video, which one is the second video. And that, I deleted them all because of the fact that I also post them on the discussion sessions. So really, all of this one, so if there's 2 or 3 of them, I combine them and I put them on the same link, I post them on YouTube and post the link for you guys in the discussion session, right where the assignment is, okay? So if you're running into the same situation, you know what to do now. I'm hoping that you guys pick up on that thing. So that's one thing. And don't forget, we have a big stuff this week, today actually, for the quiz. And I'm hoping, like I said, to get into an activity from, let me check the slide, which slide that is, from chapter 4. And that is slide 57, okay? When we talk about basically the ellipse as being, because we're going to go gravitational law, and the gravitational law talks to us about how planets revolve around the sun and they move in elliptical paths, basically in ellipses. So you're supposed to build an ellipse, and this is my rendition of that ellipse. Let me change the other camera because it's easier to look at the thing in there. So I want you guys to do that. Hopefully we will get to it today. If not, I'm hoping that you guys during the weekend, after you do your quiz, you take care of that. So let me switch cameras quickly. Okay, video, change cameras. And of course it doesn't play because of that background. Okay, so again, what I did was I took 2, what do we call them, those pins, okay? And I put them, actually, it's easier if you have some sort of a wood underneath, put them on the paper, and now bring a string. It has to be slightly longer than the actual distance between them. So when you join it, make sure it joins, gives you some room in here. How big? At least so that when you go around, don't make it too big, because if you make it too big, then you probably will run out of space on the paper, okay? So roughly around that. And then I took a marker, permanent marker, basically, and I ran it through from edge to edge. I didn't remove the cover, and oops, it removed. You need to keep it in place, okay, on both sides, okay? So if it comes out, that's no good, okay? So that's how the ellipse is. So it's the same distance from 2 points, which we call them the focal points. And then what I did is I measured the distance between the 2 focal points, and I also measured the distance from edge to edge. And they also measure and I go to the middle and I measure this distance in here. Those are important quantities in the path of planets around the sun. The sun is sitting in one of these 2 focal points. I chose this one. Right now we are in the winter, and the Earth is closer to the sun than the summer, because the summer is actually further away from the sun. This is still the sun, okay? The sun doesn't jump from place to place, stays in one place. So this doesn't exist. There is nothing in it. The second focal point, there is nothing in it. The sun is only in one of them. So if this is the sun, we are somewhere in here sometime right now. We're moving toward the summer, okay? Actually, we're closer from the spring, so we're closer in here. At this point, this is the spring, this is the fall, this is, we're going to talk about this in more detail, okay? But this is basically how we construct the ellipse in this case. You take a ruler and you measure the distances with a ruler. You measure this distance, you come to the perpendicular, and you measure this distance, and that's the key things that give you the properties of this ellipse, the path of all the planets around the sun, okay? So I'm hoping to get to that activity. If not, at item 1 of the discussion today, item 1 of activity actually that you're going to be doing at home is to follow the instructions in making your own ellipse. You don't have to have wood if you can get something else, like at least so that you can fix these 2 points. and make it at your best, okay, with the best of your abilities so that it comes as close as possible, okay, from an ellipse.
Is
And
that
post a picture. Yeah, I'm sorry?
Is that for chapter 3 discussion or chapter 4?
It's for chapter 4 and 3 because I'm going to combine them now together because I want this to basically, hopefully you guys after the quiz, you will get some measurements in here. Namely, you measure this distance, as I said. This is the distance between the two focal points, and you measure from edge to edge, which is called the major axis. And you measure from edge to edge in here in the perpendicular, and that's actually the minor axis. And you compare the major axis to the minor axis with the distance between the focal points. And all you need is just to the measurements. You take just the ruler and find how many, either centimeters or inches, whichever way you're doing it. At some point, take this distance divided by this distance, and that is going to be something called the we're going to add that as part of the assignment for other people to comment on how elliptic is your ellipse. How close is it from a circle, or is it flat, basically? It's quantity called the eccentricity. But that question is coming later. So after you post your numbers, somebody else will come and take the ratio of this distance over that distance and basically compare the different eccentricities of these ellipses and how close they are from circles or not circles. And that's because the path of the Earth is actually close from a circle. Right now, we are very close from 47 million kilometers from the sun. We are the closest to the sun. In the summer, this distance from here to here, ignore this point in here because this doesn't exist. The sun is here only. It's 152 million. So actually, these 2 points for the case of the sun are very close from one another. That's my point in here. But we're exaggerating it in here just to illustrate the points. For any other planets, this also distance is very small with the exception of Mars, which is kind of big. But everybody else is small, okay? They are very close from circular paths than elliptical paths. Okay, so the first thing that you do is make this thing, okay? Take your ruler and tell us how much is this distance between these two pins and how much from edge to edge and how much is from this side. Is this understood?
Yes.
Okay, so you're gonna get a string, okay? You're gonna get a pen or a marker or a pencil, whatever you like, it doesn't matter, okay? And you're gonna tie the string in such a way that it is slightly longer than the distance between where you fix the points in here, okay? Don't make it too tight, because if you make it too tight, you will have a hard time trying to run it around this thing. Don't make it too loose, because if you make it too loose, then it's going to be out of the outside of the paper, and then you will run out of space to draw, okay? Just barely slightly over, take the string and run it around, okay, in this fashion, okay, with a pen or pencil or marker, whatever you like, okay, and do the ruler thing. When we were in session, we used to do this activity in class. Actually, it's a lot of fun. But unfortunately, now you're on your own. Hopefully, you will enjoy it too. Okay, we're going to change cameras again. So chapter 3, let's finish that about the energy and the work and everything else, okay? Where is the... So basically last time we were actually discussing the concept of momentum, if I remember correctly, okay? And yeah, I think we were somewhere in here, and we were just about to introduce the concept of work. So we defined the momentum as basically the force times distance, and we came up with all, force times, I'm sorry, not force, it's mass times velocity, that was the momentum. and also define actually the impulse as being the change in momentum, and that is the force times the times time. Okay, the work is force times distance basically, and you have to be very careful in here what do you mean by distance, because there is all kinds of distances that you can consider when you're doing this kind of when you're calculating work. So if this is the force and the displacement, it's more of a displacement than a distance, then the work is simply the product of these two numbers. The force, so let's say, for example, you do 10 Newton and you move it, let's say, for example, 100 centimeters, or let's say, for example, let's make it 1 meter. So in this case, it's 10 times 1, which is equal to 10, and the unit for work is in joules. Okay, that's in honor of Mr. Joule, who did a lot of work in this area, and actually because we were confused a little bit about what the concept of heat was, and he showed with an experiment that heat is actually energy. Okay, and by the way, the units of energy is also the same thing as the joule too. So that's basically in a nutshell what this expression is. Okay. Now, if the force is perpendicular to the displacement like this, so if this is the distance traveled, this is a displacement, and this is the force, in this case, the work is 0. So what really the work has to do with the component of the force along the motion. So if the force is here, then all there is to it is just this amount of it that does work. The other one doesn't do work. So the key thing in here is that the force has to be in the direction of motion and really to find work, okay? So the fact that you're carrying something and moving, for example, on the same floor, you really are not doing work in this sense, in the physical sense, because you have to go to the second floor or come down from the second floor before you do work, okay? For example, this athlete, when the athlete lifts the weight, in this case, the athlete is doing work. But during the time when the athlete is holding the weight, there is no displacement in this case. So the work is 0. There is an effort, though. You have to distinguish between the two. And the effort is the force exerted by this person, and that's what makes this person sweat. Because there is weight in here. There is mass times gravity in here, which is the weight of this stuff. And that person has to provide the necessary force in here to keep them in place. And that force results in a lot of energy internally to keep that force in place. So there is effort, and that's different from work. Work needs motion. If the athlete moves this object, let's say, for example, 50 centimeters, and let's say, for example, they weigh, for the sake of argument, 200 pounds or 300 pounds, I don't know, it says in here, 25 kilos, and 25 kilos, that's 50 kilos. That's only about 120 pounds or something. Okay, so if the person lifts 50 kilos, it's clearly 50 kilos, times 10, maybe there are more, I'm sorry, I made a mistake. This is 25 times 2, that's 50, and the other side is 50, so it's actually, that athlete is lifting 100 kilos. And each kilo is multiplied by 10 to make it 1,000 newtons. So this person is lifting 1,000 newtons. And if the person lifts it from the ground up, that's about 1.5 meters, okay? Let's call it a meter, okay? So this person needs to dispose of 1,000 times 1, which is 1,000 joules. That's how much energy it is, okay? That's how much this energy is going to dispense of. By the way, all he has to do, all this athlete has to do, is just go and grab a bar, and a Snicker bar or something like that, half of it, fraction of it, that has more than 1,000 joules in it. So you have to be careful, basically, that exercises don't really dispose of a lot of the things we eat. Okay. Now, if you push on an object and the object doesn't move, does it move? Does really the are you doing work now? Does the object move? That's the question. Did the object move? No. Since the object is stable, is not moving, so in this case the displacement is 0, so there is no work. So this guy is not doing any work on the wall. But what I want you to really not confuse the two with is the effort and the work. The fact that you're pushing on the wall doesn't mean that you're not going to get tired. Okay. That's the key thing in here. So this person, you do no work on the wall. So the quantity of work done is equal to the amount of force times the distance moved in the direction in which the force acts. So there are two kinds of work. You can do work against something, or you have something do work against something against you. One of the two things. Okay. So that is really the key things in here. Of course, work will result in the change in motion in this case, which is the velocity. So the concept of energy is the ability to do work, really. That's basically what it is. It's some sort of you can convert it back into work whenever you need it, okay? So for example, an object, water, for example, on a waterfall has energy, because when it falls, it's going to turn turbines, and those turbines, basically, as they rotate, as they spin, will convert that energy of the falling water from a height to a lower level into electrical energy, and that electrical energy can come into the plug-in here, where I plug a device in here, and that device will move something, will do actually work. So in this case, both the electrical energy and the height, which is actually gravitational energy due to the gravity, has the potential of doing work, which at the end it did. Okay, so defined as to produce changes in matter. So that is potential energy actually that changes the arrangement of matter too. Effects of energy observed only if it is being transferred from one place to the other. Again, we have potential energy in here due to gravity. With a turbine, which changes into electrical energy. Okay. And at the end, we converted it into work, actually, in this example I gave. The energy and the work are both measured in the same unit, which is joules, because they are related to one another. They are not the same. They are related to one another, okay? So the fact that you have an object sitting in a height, it has potential energy. It doesn't mean that it's doing work. It has the potential to do work, okay? If you drop an object, that object can move something, okay? So if it moves something at the end, then, because now it has converted its potential energy into kinetic energy, and the kinetic energy can result in doing work on something else, okay? Then that is basically how the relationship between them. So the energy of motion is kinetic energy too. The fact that an object is moving has a kinetic energy too. So that is also another form of energy. So you don't necessarily just talk about potential energy, but also kinetic energy. So there are two kinds of energies, really. There is a potential, which is the energy of position. And there is the motion energy, which is kinetic, which is the motion. And they both will move from one form to the other. There is an exchange, free exchange between the two. But both of them can yield to work, can give you work at the end. You can convert them to work, okay? That's really the concept of energy. Now, concept of power is related to the two. I had some light bulbs earlier, I was looking at them. And that is how much work is done per unit time, okay? The first person next to my the list, at least the way I'm looking at it right now, is Andrea Reza. For example, let's see, for example, me and Andrea were asked to do work. Lifting, for example, 100 kilograms is too much for me. So I'm going to do, for example, 10 kilograms only, okay? And we're going to lift them from the first floor to the second floor. So, and the first floor to the second floor is roughly about 3 meters. So both of us are going to do this much work, 10 kilograms times 10 meters per second. That is the weight of this object, which is 100 Newton. And we're going to move them 3 meters. So that is going to be 300 joules. So both of us are going to do the same work, okay? However, Andrea, for example, takes maybe 1 minute to go from the first floor to the second floor. And I take, for example, 10 minutes to go in there and that height, okay? So there is a quantity in here that is needed to distinguish the two ways of doing the same work. It's 300 joules is the same. But for me, it takes me, what? Did I say 10 minutes? Okay. For Andrea, it takes 1 minute. So there is a quantity in here and the quantity is power. Who's got more power now? What do you think? What do you guys think?
I would think Andrea, because she did the same amount of work faster.
Faster with less time. Okay. As a matter of fact, I can tell you what her power is. It's going to be 300 divided by 1 minute, which is 60 seconds. And that's going to be 3/6. So she's doing it in 5 watts. That's the unit for the energy. So it uses the watt in here. The unit of power. Whereas I do the same thing, 300 joules in 10 minutes, and 10 minutes is 10 times 60 seconds, and that's clearly a tenth of that, which is 0.5 watts. So I have a lot less power by a factor of 10 than what Andrea does. And the same thing, proportions are actually with the time in here, this case in here. You can do the same work, but if it takes you a whole day to do just a small thing, probably your boss is not going to be too happy with you, okay? Than if somebody else who does the same thing in faster time. And that is a quantity near power. So when you go to the store, for example, and buy a 60-watt light bulb versus that, for example, that is a 100-watt light bulb, that means that this one, in every second, it's going it needs 60 joules to deliver power, to deliver a light to you. Whereas that one, in the same second, it's going to consume 100 joules. Which one appears brighter, do you guys think? Which one delivers more light? This is light bulbs, huh? So which one do you think delivers more? Oh, I'm sorry, I can't see the chat when, oh, okay. Of course, the 100 in this case is a lot brighter. Thank you very much, guys. So because of the fact that it takes more energy during the same time, obviously it's going to cost you more because the power company will charge you not the wattage, it's going to charge you actually the watt hour, which is really an energy, which is your joules, okay? The fact that you have the plug in your home, the power company should not charge you at all for it. The power company will charge you once you plug a device in it. However, I know that they charge for subscriptions and what is it called, the taxes and fees and all kinds of things. So even if you have nothing running, you're going to receive a bill at the end of the day from them. Okay, that's how they do their business. So that is the concept of power, okay? So again, I mentioned the potential energy. Potential energy is the energy of position, namely this object, when it's at this height, it has potential energy. At this height, it has potential energy. At this height, it's potential energy. And it's the same potential energy, as a matter of fact. All of it is the same thing, okay? Whether you take the object and take it the whole 3 meters up, or you go on an incline, or you go on the steps in here, you're gaining the same amount of potential energy. The potential energy is mass times, it's the weight times height, that's it basically. So if the height is 3 meters, it doesn't matter which way you do it. That's the advantage actually of the incline, which is a simple machine, is to make the effort a lot easier. It's much easier for me to go on the 5 meter incline and take this object than if I just lift it up straight up. This is harder, takes more effort. But the energy in it's the same thing, okay? That's why the incline is a simple machine. It helps us do work with less effort, really, okay? Obviously in here, where the payoff for that, yes, you're gonna spend less force to do that, but you're gonna go longer distance because it's an incline. This distance, 5 meters, is more than the 3 meters. This is 3 meters. So if you go 3 meters up, you travel less time, I mean, less distance, but you get the work there. Whereas in this case, you travel a whole 5 meters, but actually with less force. Okay, less. You don't push as much as hard as on this one in here. So the force is less, but the distance is more. So that's the trade-off. But it's still the energy is the same. So if, let's say, for example, you're carrying, to go back to the example of the 10 kilograms times 10, that's 100 Newton. So if you're taking 100 Newton up straight out, you're spending actually 300 joules on this. If you're taking it on this one, actually, you're going to go distance 5 meters. So you're going to spend actually 300 divided by, it's going to be 60 Newtons in this case, instead of 100 Newton up. So this will be 100 Newton up, and you have to fight the 100 Newton up, whereas in this case, you only fight 60 Newtons, okay? So that's slight difference. So that's why this one is a good simple machine in here. So potential energy is defined as a stored energy due to position, shape, or state. And this stored state energy has a potential for doing work, okay? Gravitational potential energy is this example in here. It's due to gravity, and it's equal to mass times weight times height, basically. So that is really the value for the gravitational potential energy. I know in this class you're not going to be doing algebra and things like that, but sometimes the numbers can tell a lot, but more than what we say. That's why I use numbers and the examples and things like that, so that you understand the point better. So this is the potential energy. The symbol for it is PE, potential energy, and its weight times height. Okay. So whether you go on an incline or you put the straight out, it's the same energy. So in the previous example, I took 300 joules. In either case, it's 300 joules. But on this one, she's spending less effort, meaning she's putting less force, but traveling longer distances to arrive at the same energy. Whereas he's putting more force, but traveling less distance to arrive at the same energy, okay? So the incline in here help you with the effort. In a sense, you do less force, albeit you travel longer in this case. Does a car hosted for repairs in a service station have increased potential energy relative to the floor? Absolutely. Case in point, what if you cut the strings where it's attached or whatever it is? It's going to fall and convert that energy into kinetic energy. You guys understand? The test in here is a car. I'm lifting it up. So it was on the floor. I lift it up. Now, whatever is holding it in there, if for something faults and stops working, this thing is going to convert that potential energy into kinetic energy, and actually can smash things at the end and change state and do work for us. So yes, okay. So the work energy theorem is really a big theorem in physics. We use it extensively and to solve problems in physics. And this is in lieu of F equals to ma, in lieu of Newton's laws of motion, actually. And it's equivalent to Newton's laws of motion. And the statement for it is that forces do work to change motion. That's basically what it is. Not motion, to change the kinetic energy of the system. So that's why it's called work energy theorem. Okay. So reducing the speed of an object is bringing it. So this really applies to everything. Okay. So the kinetic energy is by definition, like I argued last time, of how Du Châtelet argued that the kinetic energy is proportional to the square of the velocity, not the velocity itself, and quantitatively is 1/2 of mv squared. If you're bugged with the 1/2 is coming actually because of calculus. This 2 cancels the 2 in here when you take derivatives. So if you know about derivatives, if you don't know, just take it as granted, okay? To make things work, because to make that work energy theorem really match Newton's laws of motion, we needed this half, okay? Otherwise, the experiment show that the kinetic, that twice velocity, double the velocity, quadruple the impact, triple the velocity. Now that factor of impact will be by factor of 9. So that's how we knew that the kinetic energy is actually proportional to the square of the velocity. Obviously, having a bigger, more mass will cause more damage still. So that is still, m is there, but we were confused in the beginning. Is it velocity only or square of the velocity? That's where the debate is, and she settled it basically by stating it's the square of the velocity, taking the notes of somebody else who ran the experiments. But we were not sure about, I mean, that half factor came in later on when people tried to match this with the Newton's laws of motion, reconcile the two, and the factor 1/2 was needed there for this reconciliation. Okay, so if that's really bugs you, if not, just take it for granted, okay, that 1/2 of mv squared, okay? Must a car with momentum have kinetic energy? Yeah, of course, if you have momentum, that means your mv. That is what momentum is. Therefore, you have 1/2 of mv squared, okay? And the units are different. This one, again, is in kilogram meter per second, and the units for this guy is in joules, okay? So that's, so here is the work energy theorem in its glory. This is a very, very powerful theorem. As a matter of fact, it transcends this classical physics that we're doing right now and goes to modern physics, namely quantum mechanics, relativity. This is a big deal. This is one of the foundations that are used in modern physics, because other physics, they have a problem with position and things like that, but it's easy to work with this one and solve stuff with it. So it sounds like kind of easy enough. The network, the work combined of all the forces is really will be the change in the kinetic energy, as simple as that, okay? And it's equivalent to Newton's laws of motion. Whenever you see the symbol delta written, usually it means change, okay? Consider a problem that asks for the distance a fast-moving crate across a factory floor in coming to a stop. The most useful expression is, okay, here is what this is talking about. If you care about time, you really need this expression. If you don't care about the time and you just care about position and velocity, this is the equation that you need, which is the work energy theorem. The change, here is delta, the change, this is kinetic energy, is equal to force times displacement, which is the work. Okay, since this question, consider a problem that asks us for the distance a fast-moving object, my fast-moving crate slides across a factory floor in coming to a stop, then we know it was fast-moving, we know it stopped, so we know its velocity. At the end is 0, at the beginning it's something, and then the distance traveled is this one. Then in this case, this expression seems to be more appropriate, because we were not asked when this thing started, when is it going to happen, how long does it take to do, and we don't care about those terms. If we did, then this is not going to be very helpful. Actually, we have to come back in here and solve stuff here. Okay, so that's really what this question has to do with the work energy theorem. Conservation of energy, again, energy transforms without net loss or net gain in the operation. Even if you include friction, which seems to be the problem, usually all the energy is conserved in this case, but it's very hard to tally the friction. So in this case, what you have potential energy. When the object is this height, you let go of the string or you cut it or do whatever you want to. Now this potential energy is going to change, and the object starts to move now. It was at rest. It had no kinetic energy because 1/2 times mass times 0 squared is 0. So when it was at rest, the kinetic energy was 0. But now it's moving. So it definitely has kinetic energy. And as a matter of fact, it's going to impact this piece of wood, and it's going to move the piece of wood. That some of that kinetic energy already went there. It's going to produce probably damage to it. That's part of another kinetic energy that went there. It's going to produce a sound that you're going to hear. That is also actually some form of energy, because sound waves take with them energy. And it probably is going to damage this one a little. And that is actually too part of the kinetic energy that was transformed. So you started with potential energy, converted it to kinetic energy just before impact. After the impact, you have all kinds of energies that basically appeared. The only energy that was lost during that time is because this thing will come to a standstill, is again, the kinetic energy will go back to zero. But everything else will appear in here. Deformation, sound, heat, as a matter of fact, you can probably go there and feel the heat there too. And those are the three types of forms in here. Probably flying stuff too from the wood. That is actually another form of kinetic energy that's going to come out of this this whole process. So again, that tells me that the energy that I started with, PE, was converted to all these kinds of forms in here. Okay, the total energy is conserved, meaning I started with this much potential energy. Let's say, for example, 500 joules. If I tally every single piece of this joule, this energies, I will recover my initial energy. Again, I talked already about simple machines. Conservation of energy, I already stated the fact, for example, when we were talking about the incline, that the person who went on the incline and the person who was straight up, both of them spend the same amount of energy. I think the example I used was 300 joules. So the energy is the same, okay, whether on one way or the other. But in a simple machine, usually you have, for example, let's take the lever, for example, which is a simple machine, okay? You have a load in here that you would want to take, okay? And you have an effort in here that you want to exercise. So this is the effort. Force, that's what the effort is. Effort. Did I spell it correctly? And then you have a load in here. Okay. The load will travel a certain distance in here. So this is the output. And this is the input. This is what you need to do. Okay. Because of the conservation of energy, they must be equal. These two amounts must be equal. The input work and the output work must be equal, okay? But because force times displacement in this case is equal to force times displacement in this case, the force in here, the load is huge. You would want to lift an elephant, for example. You can do it, but it's not going to move much. Whereas in your case, you're going to spend less force. You're going to pull it with your hand, and it's going to actually require a lot of distance. And at the end, the work is the same. Okay? Was it Archimedes who said, give me a lever and give me a point where I basically really go fulcrum, and I'm going to, this is called the fulcrum, by the way, and I will lift the wood, because it doesn't matter what the load would be, as long as you can have a point where you put the support there, you're fine. You can have a, so this is a simple machine. This is the lever is a simple machine. The incline is another one. We already saw two of them. So this is the advantage, really, of a simple machine. You would want to have less force in here. You don't want to spend a lot of force, but the payoff in here is that the distance you travel is a lot. For example, on the incline, you travel 5 meters instead of just 3 meters. But instead of spending 100 newtons, which is the big load in here, you only move at 3 meters in that example on the incline. Same thing with the lever in here. Same thing with every single machine. So this is really what you want from the less effort. You don't want to spend a lot of force. So that's really the advantage, if you wish, of a simple machine. This is its efficiency, okay? This is called the mechanical advantage, by the way. The ratio of this force over that force is the mechanical advantage. What is the advantage of this machine is how much force can you get out of this effort, okay? So this comparison, we did it already. Conservation of energy. So this is a summary of everything that we've been talking about. Unless here is again about machines, machine and device multiplying. force or changing the direction of the force. Here's another simple machine that that we can use also is the pulley. You have a load and you have the effort. In this case, they were equal. So the load in here, let's say for example, is 100 Newton, and the effort is going to be 100 Newton. Okay. So that the pulley did in this case is change the direction of the force. That's all. So instead of pulling up, you're actually pulling down. That's all. So the pulleys are also are simple machines. But the combination of pulleys, they can be both. They can change direction of the force and actually reduce the effort too. And those are actually compound machines. They are not simple machines. But we're talking only about simple machines. Okay, again, this is the lever. Okay. And the example in here is just a numerical example, similar to what I gave you guys. So the efficiency of the first of all, the efficiency, I probably gave it confused it with the advantage, the mechanical advantage. The efficiency is how efficient it is, and because of friction, because of all of the waste, usually the efficiency is less than 1. It cannot be more than 1. First of all, you cannot produce more energy than what you put in it. Number 1. Ideally, the best you can do is 100% efficiency, meaning that you put 100 joules, you get out of it 100 joules. So those scenarios that I gave earlier on the simple machine, for example, on the person who went on the incline versus the person who shot it straight out, is actually an ideal situation. The real situation, the person who goes on the incline will spend more than 300 joules versus the person who went straight out. And that is how efficient, in that case, the incline is. Okay. So the efficiency is the work done over the energy used. And in this situation, you're going to multiply it by 100 to get it into the percentage, because it's going to be a fractional number. So the efficiency is going to be always less than 1. Okay. And the mechanical advantage is the ratio of the efforts, the effort and the load over effort. Okay. So that is really what we want from the simple machine, because we're going to lose energy. So if the energy is all there is to it, then there is no point of having simple machines whatsoever, or any machines whatsoever. But machines which are more complicated than simple machines are needed for other purposes, like for example, to reduce the effort. So it's much easier to go on an incline. That's why in loading docks, for example, and things like that, they have a lot of incline planes there for people to load things on trucks and things like that, because it's easier to do it that way with a dolly and you have things. Otherwise, lifting things up and down, it's really hard. Okay. So again, these are mechanical machines in this case. So again, this is an example. A certain machine is 30% efficient. This means that the machine will convert 30% of the energy input to useful work and waste 70%. 70% of the energy of the input work, 30%. Oh, no. So this is a question. I'm sorry. A certain machine, 30% efficient. This means that the machine will convert 30% of the input of the energy input to useful work, and 70% of it will be wasted. That's correct. Okay. It has to be A. Because 30% efficiency, that means that 3/10 of the work that is needed will be useful. So this is useful over basically needed. So 70% is wasted from the needed, and 30% is useful. Actually, that's basically what this thing is saying. Sources of energy, at least on Earth, mainly it's going to be the sun. All forms of energy that we have them, they're basically the sun. First of all, the obvious one, the daily heat of the Earth. And then the wind and the weather is really powered by the sun itself. The hydrocarbons are actually plants that grew in the sun a long time ago. And now, I mean, what I mean by that is oil and gas and all of this natural resources and what is it? Anyway, all methane, all kinds of things that are actually from activity of the sun a long time ago, with mainly plants that now we're using them in terms of energy. I would say the vast majority of the energy. Is this sound from my system or from your system, guys? Sapida, okay. Anyway, the point being in here is that that's the sun is the main source of energy on the Earth, except it's the core of the Earth. The core of the Earth has other forms of energy, which is really your radioactivity. But other than that, which is a small fraction, meaningless for us, the sun is the source of most of the energy on the Earth, namely most of the life on Earth, okay? And again, this is how you extract energy, in case in point in here, dry rock, geothermal powers, and other forms of energy from the sun. We have photovoltaic panels, hydroelectric turbines, the waterfall that it was on for producing, for example, on the Hoover Dam. That is actually a process that is weathered. That is actually the weather, taking the water from the oceans and going through the cycle of the water. And the source for that is actually still the sun, okay? Wind turbines and those biofuels. So that's basically some of the energy sources. Man, this lecture is very long. So again, we store energy in other forms, for example, electricity, synthetic fuels, and hydrogen. Now there are some hydrogen-powered cars, and still hydrogen cells are not really that popular compared, for example, with electrical cars. So hopefully the next cars that I'm hoping at least to go into ones that run out of hydrogen. Okay, again, this is how the process you make it with the creation of hydrogen using just a simple battery and H2O. You basically separate the oxygen from the hydrogen in the water molecule. So those are chemical processes. And that's how you get the hydrogen and use it as fuel for powering other things. And, this is actually solar panels. Anyway, this is in a nutshell chapter. The main things that you take from this chapter is the concept of energy, concept of momentum. The impulse is not as much in terms of your daily applications, how energy is related to work. That is critical in here and for you guys. And the two types of energies, namely kinetic energy and potential energy, those are the key concepts that you're going to take from this chapter, okay? If you guys don't have any questions, I'm going to move to the next chapter because I promise you guys that we need to get into that activity, hopefully. What is the other screen here, man? Show all windows. Okay, here it is, all the way to the bottom. Anyway, so chapter 4 deals with gravity, projectiles, and projectile motions. Mr. Newton was sitting one day under a tree, and an apple fell on his head, and then he came up with an expression that basically says F equals to minus G. Let's ignore the minus for right now. Let's just take the magnitude, okay? G times M1 times M2 over distance squared. Does this sound credible? Is this? Somebody put something in the chat. It's a good idea to rent it, Marianne. Okay. So let's continue with this discussion, and we'll get into that point hopefully. So let me go back into my points in here. So basically, Mr. Newton, according to the stories, was sitting under a tree, okay, and an apple fell on his head, and all of a sudden he came up with this expression. Does this sound plausible to you guys? The story? Maybe. This is actually more of a myth than reality. It's not, this is not how it happened, okay? He came up with this expression, and he studied the apple, really. I mean, he looked at the apple too as an example, but there is more to it. He was not really like that. It took him actually 4 years before he came up with this expression. He made a big argument for it. This is the universal law of gravity. It's this expression, okay? Basically what this says is, if I have two masses, M1 and M2, Earth and the moon, Earth and the sun, an apple and the earth, it doesn't matter which one you have, they have masses, and the distance between them is r. This is the distance squared. This number is just a number. It's just 6.67 times 10 to the negative 11. It's a tiny number. He needed it because he wanted to reconcile his work with Mr. Galileo, okay? So because he knew the experiments of Mr. Galileo and his theory of gravity, he wanted to put them together, and they match because he knows how fast the apple falls on the earth, not how fast, how much accelerated it is. And this one also will give you an acceleration. So he wanted to match his acceleration with that of Mr. Galileo, who did the work before him. So he chose that value for g. So that's a constant, just like the speed of light, just pi, like any other constant that you encounter in your life. So that's this number, okay? And this is the force, the same thing that is in Newton. So that's basically what this expression is, okay? And that is the universal law of gravity. This is actually universal because it governs everything, whether it's a pen in my hand, myself and the earth, an apple in the earth, me and the apple. They're all attracted by this force of gravity. The earth and the moon and the astronauts who went to it, and also from the earth and the sun, Jupiter and the sun, the moons of Jupiter and Jupiter itself, and the earth, and I mean the sun itself, and the galaxy as a whole thing with all of this bunch of stars in it, and then the galaxy and the other galaxies, Andromeda galaxy and other galaxies in the universe, and everything that you can think of. As long as you have mass, you are allowed to play this game. So this game is open for everybody who has mass. And since everything that we know of has mass, you can play it. So this is an open game. It does not discriminate on you based on anything. As long as you have mass, you're allowed. If you don't have mass, like the photons don't have mass, you cannot play this game. You guys understand? If you have mass, you're in. If you don't have mass, you're out. Does this make sense? So again, the inverse square law is this number, okay? And then the weight and weightlessness, basically that concept, and I told you about that experiment that you guys can do. Projectile motion basically is because of the force of gravity. So if you take a rock, for example, and you throw it, it's going to follow this curve, okay? So that's what we mean by projectile motion. So it needs an initial velocity, and it's going to go and fall somewhere, and this distance is the range of the projectile, okay? And the time it takes to go all the way come back is the time of flight. So if you are trying to build some sort of a projectile, I know we have on campus, and they told me, the dean told me about it, and tomorrow I'm going to campus hopefully to see that, is the, we have a catapult there that was donated by the US Navy. So I'm gonna go and look at it and see if we can play with it, okay? So, and then we have fast-moving projectiles and satellites. That's also the satellites are attracted to the Earth, just like the moon is, okay? And that actually gave us an idea in here. We can do a satellite. If here is the Earth, okay? And we have a satellite in here. And if the Earth does 24 hours to spin around its axis, goes 24 hours to go around its axis, we're gonna make this satellite also spin in 24 hours. Once around the Earth. Can you imagine this? Isn't this clever? So we have an Earth in here spinning 24 hours. It goes once. I mean, this time around tomorrow will be exactly as we spun right now in 24 hours. And then if we have a satellite that is sitting actually in the sky that also does the same rotation in 24 hours, so that satellite, as I am moving, will stay in orbit all the time above my head. You guys understand? Do you guys know what these satellites are used for? Does anybody know what these satellites, that they don't change location? Cell reception, not so much. They are actually, we use towers mainly, at least. Fuel, no. They're used actually for finding you on Earth. Do you know what they are called? Those devices? Yeah, but they have a name. They're on your cell phone. Your cell phone connects to them all the time if you're using any navigation. GPS, thank you very much. Have a nice day. That's what they are useful for. Used for. Okay? So they're used for GPS, global something satellites, positioning satellites, GPS. Okay? So they're used for that purpose because as your phone locks on one of them, you need 3 of them to be triangulated, basically, to know exactly where you are. So your phone at least needs 3. Usually it connects to more than 3, but 3 is good enough so that they, and as the Earth spins, you're going to see them all the time above you. So that's, again, a clever way of using this thing that Mr. Newton came up for, that derived for us to use. That's really a very nice thing. Okay. And this is the activity I want you guys to do. Elliptical orbits, because all objects go in elliptical paths around any, I mean, that's the standard path, okay? An ellipse, I mean, a circle is an ellipse where the 2 blue points, as I was showing you earlier, collapse on one another, that's all. The distance between the 2 pins is going to be 0. That's what a circle is. So a circle is actually a special case of an ellipse. Ellipse is more general. It has 2 focal points. The circle is an ellipse where the 2 focal points are the same points, which is the center of the circle, okay? And we're going to talk about the escape velocity, and that is to help Mr. Matt Damon get out of Mars, because if you guys remember, he was stuck in there, and he needed to get to his rescuers. So the escape velocity on Earth is 11.2 kilometers per second, and Mr. Damon's escape velocity is actually less because he was stuck on Mars, okay? And that is basically what the escape velocity do. It has to do with this expression too, okay? It has to do with this force too. Does this make sense to you guys? Did you guys see Mr. Damon getting out of, Matt Damon getting out of Mars? Anyone? You didn't see the movie? Martian? Surprised. It's a fun movie. Okay. Well, that's a good time to go and watch it too. I think it's on probably Netflix or something. Here is basically how the legend has it, okay? And I emphasize the word legend in here because it's not true. That Mr. Newton was sitting under an apple tree and realized that the force between Earth and the apple is the same as that between the Earth and the moon and planets and everything else. No. The real story is that he basically, because of the plague that hit London, which is similar to what we are going through right now, actually, where a lot of people basically were in, he was in college at that time, and he already came up with his 3 laws of Newton basically at that time. And he was a student, and then they asked him, okay, everybody leaves college and go home. So he went to the countryside, and during that time, he was basically sitting doing not much until I think, I don't remember exactly who with, I don't know, I forgot, I think it's Haley or somebody, who gave him the work of Mr. Kepler. Mr. Kepler came up with 3 laws of motion for the planets around the sun, basically. And in his laws, Mr. Kepler came up with 3 laws. The first law says that all the planets, as they orbit the sun, they go in elliptical paths, just like the path I'm asking you guys to draw. The second one is, he said that let me change a thing in here to explain Kepler's laws, because actually they are beautiful laws. Since you are at this level, you really need to know them too. Okay, what is my stop sharing? Why did I stop sharing? I'm sorry, I didn't mean to do that. I meant to change cameras quickly. Video, change camera, and now let's remove the background again. Okay, so basically this is the first law. The first law of Kepler basically states that all planets orbit the sun in elliptical paths, okay? That's one of them. And then it says that the area swept in the same time is the same. Meaning if it takes you 1 week to go from here to here, for example, to go through this path, this angle now is the one I'm trying to draw, and it takes you 1 week to go through this path, for example, remember, it's from this distance to the sun, these areas are the same. That was the second law of Kepler. The third law of Kepler was kind of complicated a little bit, and it has to do with the year. It goes around once around the sun. And that year, that period is called the period, which is a year for the case of the Earth. So the period, which we usually use the letter T for it, squared is proportional to this number cubed. It's proportional, not equal, because one of them is time, proportional to the semi-major axis cubed. So that's kind of mysterious. Three laws, basically. The first one, they're elliptical paths. And that really was a problem for the church because they didn't like that at all, because of the fact that people believe that the heavens are perfect and there is no such a thing that the most perfect shape in the universe is a circle. So the paths must be circular. So that was the argument that they have. And the only reason why we have mountains and we have rivers and we have problems on Earth is because of the sin of men. That's basically the argument that was presented by theologists at that time. And this path in here contradicts that, and that was a problem because this is not a circular path, it's actually an elliptical path. I know it sounds silly right now, but that's exactly what was going on at that time. And then the other thing in here is that this area in here spent in 1 week, for example, same amount of time, this area, and this area spent in the same amount of time are the same. So if this is 1 week and this is 1 week, these areas are the same, okay? So that's really the second law of Kepler. And that means the object in here has to be moving very slow. The planet has to be moving slower than in here. It's moving faster to make up that true, okay? And the third law was this one, that the time it takes for the planet to go once around the sun is proportional, not equal. I mean, it's of the same order. That means the ratio of this number over that number is fixed, doesn't change. And what I mean by semi-major axis is this distance. This is the distance, the so-called semi-major axis, okay? Because I asked you guys to measure the major axis, which is from point to point. Half of that is the semi-major axis. From here to here is half of that, okay? So this is called the major axis. What I mean by major axis from here to here, basically where the fattest of the ellipse is. And when it's the shortest of the ellipse, which is this one in here, this is the minor axis. What is working in here is in this case is actually the major axis in this expression, okay? So that's how Mr. Kepler came up with this law. So Mr. Newton was asked, hey, can you explain these three laws for us? He came up with an explanation right away, but it took him a long time to publish it because he was really struggling with the math at that time. There was no calculus, so he ended up inventing calculus. So that's basically how the actual story is. So this is an approximation. So what he said is the following. First of all, the fact that asking me to interpret the planets, how they go around the sun, ignore that for a moment. He said, let me focus on the moon, because I think that what causes the moon to go around the Earth is the same force that causes the Earth to go around the moon, as the Earth to go around the sun. That's one thing. And he's argued not only that, but I think what causes this apple to fall is the same thing that causes the moon to go around. Because if I tether an object into a string, for example, and spin it, that object will go around this axis of spin. So it seems like the moon is retained in here in its motion around the Earth by that same force that causes the apple to fall. So the moon in actuality is falling toward the Earth, but it's catching itself as it's falling because of the fact it has a speed, that's all, okay? And from there, he came up with how this worked together. So he knew the value of little g that Mr. Galileo has measured, 9.8 meter per second. That is how the acceleration of the apple toward the Earth is. And he actually can calculate what the acceleration of the moon around the Earth, because you know the moon goes around the Earth once in lunar month, which is about 30 days, okay? So you know its speed. At that time, he knew also the distance from the Earth to the moon because it was measured a long time ago before him. So from there, he was able to calculate the acceleration of the Earth around the moon around the Earth, and he came up with this inverse square law, okay? So in ancient times, Aristotle and others believed that the stars, planets, and the moon moved in divine circles free from forces. And that's basically how the argument that I'm trying to make in here, okay? We knew that the moon falls around the earth. So this is basically how the argument is. So the moon is actually falling toward the earth, but it's moving. So it's moving, and as it's moving, it's falling with the same rate so that it always stays in circular path, okay? So that's basically the argument for it. The mathematics is not really hard to do, but that's basically the interpretation for this one is. So again, as I was saying, he came up with the comparison between the acceleration of the Earth and the acceleration of the moon, and he came up with the argument that that has to be proportional to the square of the distance because, and at that time, that's really why he ended up inventing calculus, because he used for the distance between the apple and the Earth, he used the radius of the Earth. He didn't use how far the apple is from the surface of the Earth, which is about 1 meter to 2 meters, but he used the surface of the radius of the Earth. And for that, he had to basically come up with an argument that he later on, but it was later on formulated as calculus. And that's basically how he invented calculus too. So that's one thing, the square distance. The other thing also was the masses, because he's saying that if I double the mass of the apple, now of course the force doubles. So this force is proportional to the mass of the apple. Now, from the vantage point of a worm living on the apple, it's actually the Earth falling on it. So this force actually must be proportional, because if there is a worm living on the planet apple, and while the apple is falling from our vantage point on the Earth, actually the Earth is actually falling on the apple on the other from that vantage point. If you're living on planet apple, so basically that's how we argued also the two masses in the numerator, and that value of g there was needed so that his number for the acceleration he calculates for the apple matches what Mr. Galileo has done. It was really a clever way of doing things. It was really amazing. Okay. Now you know the real story of the apple and Mr. Newton. Okay, did not fall on his head. I mean, I probably will try tomorrow and sit under an apple, basically go to an apple grove and sit there and see if I can come up with something similar. Do you think I can? Do you think I will? You guys have faith in me? No? I don't either, so don't worry about it, okay? No, I think Alyssa, you're saying just to, I don't think I would come up with something if I sit under an apple tree, okay? No. I don't think that Newton also did anyway, so that's how he came up with. He was a clever man anyway, so. And he was very young at that time. He was in college when he came up with all of this wonderful stuff. Okay, again, that was one of his major contributions, is that law. It's probably more, I mean, F equals to ma is actually, and all of the three laws are important too, and they're the foundation of all of mechanics. But that one also is a major, major interpretation of the gravity. As a matter of fact, and probably we don't have time for that, but maybe down the road I can tell you about how I came up with a better theory, okay, involving basically something else, okay, for how the planets move, okay. Of course, it's not serious, but I'm just, okay. So Newton's most celebrated synthesis is of earthly and heavenly laws. I mean, he was able, because look, this is the problem that with some people they might come up with, and I met some guy before in the past where he told me that he has a better theory about law of gravity, but he couldn't do much with it. If Mr. Newton, all he did was explain the work of Mr. Kepler, that's not good enough in science. And he did explain it. If all he did was just to explain what Mr. Kepler's laws were, and he did with this law, okay? All three laws of Kepler, you can derive them from this one. That's not good enough. You really need to do something else in science and physics to really, for your theory to be true, to be acceptable. And for him, one of the conclusions that it came immediately, first of all, that proportionality between t squared and a cubed. That's one thing. But also immediate, and that has to do with the mass of the sun. So he was able to measure the weight of the sun, something that did not occur to anybody's mind before. So he could weigh how big the mass of the sun is and how massive the Jupiter was without actually going there, using that, his theory. And also, Halley, when Halley looked at the comet that arrived at that time, based on the work of Mr. Newton, he predicted in 76 years it's going to show up again. Sure enough, to almost within a day, the comet came back. So if you can do a theory and explain something that might happen in the future, something that is actually go beyond the work of an experiment that was done already, then that theory becomes acceptable. That's exactly what the genius of this stuff is. So that's what the worth of the theory is, and that's why community later on accepts it. So it's not just coming up with any silly explanation, even though probably it sounds mathematically beautiful, but it's not good enough. It has to do stuff for us. Okay. So his mainly contribution is the earthly and heavenly laws, the fact that that law is universal. Obviously, the bigger the mass, the higher the force. The closer the object to the mass, the higher the force. Okay, the closer the distance is, the higher the force. That's what this law is saying here. And this distance square has to do, for example, if you take, for example, a candle and light it, and you're closer from it, there is a lot of light. But if you move away from it, that drops like 1 over distance squared. This is one of the most amazing things. And it's probably a coincidence that that distance squared, it's not a coincidence because of the fact that we're living in this three-dimensional universe, and objects, as they move in a surface, they tend to spread throughout bigger space. I mean, if you move away from the light, from the candle, very far away, you're not going to see the light at all, because the light now is spread over bigger and bigger and bigger surfaces. So in this case, it drops like 1 over distance squared. And when you are closer from it, the light is more powerful and it's going to shine more. Okay, so that is basically the argument in here for it. And this is the mathematical representation of that square law. The closer you are, the stronger the force. The further you are, the weaker the force. And it's not just weak, it's 1 over distance squared weak. That's basically what this thing is. We're going to come back in here at some point, probably in the future, and talk about dark matter. And this is the essence of dark matter. This is how we discovered and we knew that there is dark matter in the universe. Again, we're talking and applying about if you double the mass, you double the force. If you quadruple the mass, basically double both masses, you quadruple the force. If you come closer by a factor in half, you quadruple the force, because 1/2 squared is 1/4 squared. But take it in the numerator is going to be 4 times. As you come closer, if you were at 4D and now you come closer at 2D, in this case, the distance is doubled. The force goes away from this value all the way to 4 times of what it was before. And vice versa. If you move away, the force will weaken. Okay. So all of these discussions are dealing with that. And as a matter of fact, this is the value of G. Okay. This is just to fix things. Okay. This number is to fix things. Here is the beauty of this number. Is this number 10 to the negative 11. That means it's 0.00. Let me count it. 0.00000000067. It's a very tiny number. Had this number been any bigger than what it is now, even by slightly an amount, the whole universe would have collapsed and we wouldn't be here to talk about it a long time ago, because this value is too big. Had this been a number any smaller, we would have flown apart a long time ago, and the planets and everything else, and even the people would not exist. So this number is just what the doctor ordered for us to come in here and talk about it and talk about everything else. So this is one of the things that is unique about our universe, where we live in. So that's really this number. It's one of the secrets of the universe. Okay, this constant. Again, the way he arrived at this number, because he knew the work of Mr. Galileo, 9.8, and he had to match the two expressions, and that's how that number emerged from there. So the universal constant G, which links force to mass and distance, is similar to the familiar pi or G. No, it's not familiar to this G. This G is different from planet to planet to planet to planet, so it's not correct, okay? Acceleration due to gravity, that's g actually. Speed, no, it's not. Of a uniform motion, no, because that's different on the people and how fast they move. It's closer to pi, and pi is just the ratio of the circumference, so that's a number, okay, at least on this planet, and that's how you can think of this g in here, not on this planet, in this universe where we are, in this geometry, okay? But g, that's basically what it is. But don't forget, pi is an irrational number, and this is an experimental number. So this is actually an actual number, and actually it's an irrational number, which is kind of weird. But this is actually an experimental number that seems to be constant everywhere in the universe that we live in. Okay, weight is the force exerted, and I think we talked about this. That's mg, mass times gravity, okay? Weightlessness is a condition wherein the support force is lacking. The way we check our weight is we stand on a scale, and that scale will give us the support force. If there is no scale, if there is no support force, then in this case, we feel weightlessness. We never feel really our weight at all, no matter what. The only thing we feel is actually the scale. That's all, how it's pushing back on us. So if we remove the scale and we're in free fall, then in this case, we don't feel our weight, and we are in the state of weightlessness. It doesn't mean we don't have weight. We have weight all the time, whether we have the scale pushing back against us or not. We feel the weight. I mean, right now, if I'm sitting on a chair, I feel my weight. How do I feel it? It's because the chair is pushing back. That is why I feel my weight, okay? If I'm moving, that I feel my weight. But if I am jumping, at least during the jump in or out, it doesn't matter, I don't feel my weight. So during that time, I'm in weightlessness, okay? And this is the example I told you guys a long time ago that we can go in business with. So this is zero weight because the support force doesn't exist. In this case, there is weight, normal weight. When it's accelerating upward, you feel more weight because you are pushing on the scale, and the scale will push more. So you feel more weight. The weight never changed. It's the same in all four cases. But your state of whether or not you feel weight or not, that changes. Now you feel your own mass times gravity. Here, you feel more than mass times gravity. As a matter of fact, you feel more mass times gravity plus the acceleration of the scale, acceleration of the elevator. If you're coming down, for example, in this case, you feel less weight because it's mass times gravity minus the acceleration with which this thing is. And if this acceleration is exactly g, meaning you're in free fall, g minus g is 0, and you feel weightless completely, okay? So that's a good business proposition. Go to the bank and get it funded, okay? Okay, I know the only thing that I mentioned today has to do with this activity, because I really know that you guys have an exam. So I want you guys to focus on the exam right now. And all of these slides is basically about the upward acceleration, this explanation of exactly what I was talking about. I mentioned the projectile, and probably we're going to come back to the projectile when we meet next time around, because we still have less time now to finish this. So this is the projectile motion. All of these slides are about the projectile and how the projectile happens and all of that. But let me get into the slide that I talked to you about, and that is the elliptical orbits as part of Mr. Kepler's laws of motion for the planets going around the sun. And this is true even for the orbit of the satellites, for anything, okay, because of the universal gravitational law, okay? So the oval path followed by a satellite, the closed path taken by a point that moves in such a way that the sum of its distance from two fixed points is called, those points are called the foci or foci. It doesn't matter which way you say it, both of them are correct, okay? This is a focal point, this is a focal point, both of them are called foci or foci, however you call it. This distance actually from here to here is fixed, it doesn't change. This is actually what the path is. It's the path of all the points that are equidistant from 2 points, from two focal points. Whereas the circle is going to be from only 1 point, which is the center of it, okay? So that's the distinction between this one and the circle. Okay, here is your task again. Let me, where is my pen? I still have a pen in here somewhere. Okay. First of all, draw the ellipse, following the instructions that I showed you. Measure measure the major axis, this distance. Okay, that's step 2. Step 3, measure the minor axis.
Are you writing on something? Because we can see you.
I'm sorry, I thought I'm showing the slides. Why it's not showing the slides? Share. You guys, are you seeing the slide or not?
Oh, okay, yeah.
Okay. Okay, so the measure the minor axis, that's the third thing. And the fourth thing is measure the distance between the focal points. Okay, so the minor axis is this one. So this is this distance from here to here is the minor axis, and this distance is the last distance you're supposed to be measuring with your own ruler. You guys understand the task? And post it in the discussion with a picture. Post a picture in your measurements.
Which discussion board do you want us to post that in?
It's going to be a combined discussion. I did not fix it yet, but it's going to be fixed for both chapter 3 and 4 together.
Okay.
Okay. Guys, understand what the task is? Slide 57. Everybody's good? Yes or no?
Yes.
Okay. At least we have 2 confirmations here. Okay, very good. 3, 4. Okay, I'll see you guys next week. And please let me know if there's a problem with the quiz or something like that, okay? See you guys. Let me stop the recording.